Okay, so this is what we call kind of the classic wedding cake problem. It looks like a wedding cake. It's tiered. We have different cross-sectional areas. We could have different materials. And when we are looking this, we have aluminum is the aluminum member ABC, so it's all aluminum, supports a load of 28 kilonewtons at the top. Determine the value of P such that the deflection of C is 0. So we want the overall delta to be equal to 0. So I know that it's all aluminum. We want delta at C to equal to 0. So that's going to be my delta from C to B plus my delta from B to A. Okay, so as we have loads in here, A to B is going to have some sort of deformation, D to C is going to have some deformation. We need to calculate P so that at the end of the day, when we add up delta CB plus delta BA, it equals 0. So if this one's in tension, it's going to have to be in compression. Okay, I also know that for aluminum, I have an E of 70 times 10 to the 9th Pascal, which is a Newton per meter squared. So remember, I just for consistency like to put everything in Newton per meter squared. I have the area of BC is pi over 4, and its diameter is 32 millimeters, which is 0.032 meters squared. Area of AB is also circular, and it has a 50 millimeter diameter, so 0.05 meters squared. The length of BC initial is 1 meter, and the length of AB initial is 1.3 meters. Okay, so this is kind of my given starting values, and now we need to work on the problem. So I know that overall I want it to be 0, so I need to calculate P to counteract that 28, and it's not going to be just 28. Okay, it's because we also have the reaction down here. So the first thing we always do is we always start with equilibrium, and we need that free body diagram to get started. So I'm going to take my post-it note, and I'm going to start from the top and come down. I'm going to make a cut. Okay, so I have, here's my little segment. I have 28 kilonewtons, which is 28 times 10 to the 3rd newtons, because again, I like to have everything in proper units. I don't have to worry about units when I'm setting this up. So I have the force from B to C. I can sum forces in the y direction equals 0, and I can see that force BC is a positive 28 times 10 to the 3rd newtons. So it is indeed a tension member. Now I'm going to go back to our picture here, and I start at the top, so I have to include all of this, all of that. Oh, now we're in B to C, or B to A. So my free body diagram has to look like this. Everything that was above. So I have the top part. Here's the top part. It is being loaded with 28 times 10 to the 3rd newtons. And then I have part of the bottom part. It doesn't matter. I'm just cutting it somewhere in there. I have this force P that I don't have the value. And we assume everything in tension, so I have the force of AB. Okay, so now if I sum forces in the y direction, I get 28 times 10 to the 3rd minus P minus FAB equals 0. Okay, so that force that's in AB equals 28 times 10 to the 3rd minus P. Okay, and the reason I'm writing it as the force equals something P is because when I come over here to do delta, I mean, what is delta? Delta is force in CB, length in CB, area of CB, E of CB. Okay, force of BA, length of BA, area of BA, and E of BA. So I need to have everything in terms of what these are. And I have written, because of equilibrium, using equilibrium, I have written the internal force of A to B in terms of that unknown value P. So now we can start. Okay, we did our equilibrium, we did free body diagram, so now we go to deformation. And I know that delta C has to equal 0, and that's going to be the sum of my deltas, which is the sum, which is CB plus BA. Okay, so 0 equals, you can write this out, FCB, LCB, ACB, ECB plus FBA, LBA, ABA, EBA. And if I wanted to, I could go ahead and pull out 1 over E, because they were the same material, and multiply over there. So we just got rid of the material. It doesn't even matter. So I have 0 equals FCB, LCB, okay, pi over 4 times 0.032 squared plus FBA, length BA, over pi over 4, 0.05 squared. Well, I can now pull out pi over 4 and cross multiply, so that goes away. So I'm left with 0 equals FCB LCB over 0.032 squared plus FBA LBA over 0.05 squared. And now I can start plugging in. FBC is 28 times 10 to the third newtons times that original length of 1 meter divided by 0.032 squared plus, okay, FBA is 28 times 10 to the third minus P. That length that we have for AB is 1.3 meters divided by 0.05 squared. Okay, and this equals 0. And I can simplify, so we're going to say 0 equals 28 times 10 to the third times 1 over 0.032 squared plus, well, I'm going to take 28 times 1.3 and then minus P times 1.3. So I have 28 times 10 to the third times 1.3 over 0.05 squared minus P times 1.3 over 0.05 squared. Okay, so now I can combine these two terms, and move them to this side of the equation using algebra. Okay, and I get, where's my calculator? We get 28 times 10 to the third, 0.032 divided by a very, very large number. I get 28 times 10 to the third times 1.3 divided by 0.05 divided by a very large number plus. So when I move it over, I get negative 41903,750 equals negative P times 1.3 over 0.05 squared. Okay, the negatives go away, and I'm going to cross multiply 0.05 times 0.05, and I'm going to divide by 1.3. Okay, and when I do that, go to my next piece of paper here. And when I do that, I find that P equals 80,584 newtons, which is 80.6 kilonewtons. So what does this mean? What did I just solve for? This means 80.6 kilonewtons. that if I apply 28 kilonewtons here, and I have that times this length, then I need to apply 80.6 kilonewtons here, and this material and length, in order for my delta to be 0. Okay, that means that my delta for BC, which is going up, equals the delta for B to A, because it's in compression, which is going down. Okay, and so this delta of AB equals the delta of BC, so the overall is at 0. So now, if I want to find the deflection at B, so what's happening here at B, okay, then I can look at, sorry, need a much more bigger desk and a different camera. Okay, so if I want to find then the delta at B, well, I can look at from A to B, it's fixed. And so if I look at what's happening with A to B, okay, A to B is going to give me what's happening at B. So A to B is going to be force AB, length AB, area AB, modulus AB. So what do we get? I'm going to get, oh, well, the force in AB, remember we have that equation, was 28 times 10 to the third minus 80.6 times 10 to the third, okay, and it ends up being negative, which makes sense, we're in compression, times 1.3 meters divided by pi over 4.05 squared, that's in meters, times 70 times 10 to the ninth pascals, which is Newton per meter squared. So I have newtons, meters, meters, Newton meters. My units are working out, and that's going to end up giving me a delta in meters, which is going to be like a very teeny tiny number. So what I can actually do is, well, how do I convert that meters? How do I convert meters to millimeters? Well, I know that there are 1,000 millimeters per meter. So I'm just going to go ahead and put that 1,000 in there to change my units from meters to a final unit of millimeters. And I get that delta A to B is negative 0.497 millimeters, which is 0.497 millimeters acting down. Okay, and again, I'm going to show direction, because what does negative mean? Well, what was I calling positive? What was I calling negative? What's up? What's down? Show me what happens. The connection at B is going to be displaced downwards, 0.497 meters. Okay, and that is it.